rest of 12.2 today. And you'll see that homework is opened up. Remember, that one's not due on Sunday. That one will be due next Sunday, but that first part will be what you have for this week. Along with anything else we had. I don't know what else we had this week. Maybe 12.1 is due on, or was that already due? I don't know, guys. You have some homework due on Sunday. I'm losing my mind a little bit. So let me go ahead and share my screen. I've got some examples ready for us to work, and I will show you what we're going to do with that second derivative. Okay, so you should be able to see my notebook screen now. Let me get my pen. Okay. Ooh. Okay, guys, so I've got the notebook. I also have written down some examples we're going to work through so I wouldn't forget them. Oh, Gracie girl, if you need to go outside, then just go. Okay, so we're going to start with this one. All right, so let me try to remember that while I go to the blank page. Negative x cubed plus 3x squared plus 9x plus 2. I think I can remember that. So I've got f of x equals, okay, I already wrote it. Negative x cubed plus 3x squared plus 9x plus 2. Let me make sure I got it right, because this one, if I'm right, works out really nicely. Okay, I think we're good. All right, so here's what I want to do with this problem. I want to take the first and the second derivative. Obviously, guys, my goal is the second, but we have to go through the first. So on this problem, what we're going to do with that derivative is we are going to find all or any, there could be one, there could be multiple inflection points. So we talked about an inflection point last time. We never found any. Gracie, just go. You know how to open the door. You do it all the time. Okay, so we haven't found any of inflection points algebraically, but remember, to find inflection points, you want to set the second derivative equal to 0. So it's like finding critical points, but remember, critical points come from the first derivative and inflection points come from the second. So I am going to find all inflection points, and then I'm going to find all the intervals of concavity. So remember, we talked about how the second derivative tells us the shape of the graph, the concavity, if it was concave up or down. And we talked about if the second derivative of your function at a point is positive, so you put in a value for x and you get a positive second derivative, that means that your graph there is concave up. So positive goes with up. And remember, concave up graphs kind of look like a bowl. And if your second derivative at an x value comes out negative, that means at and around that x value, your graph is concave down. Which, for lack of a better way to put it, it's like an upside down bowl. So I spelled intervals wrong, you guys. You know what I was meaning there. So intervals of concavity. So with the first derivative, remember we found increasing and decreasing intervals by using the first derivative, because that's what that tells me. So we're just going to do a similar thing, just using the second derivative instead. And when we get that positive and negative, it's not going to mean increasing or decreasing. It's going to mean concave up or concave down. So let's get started. That's what I want to find on this one. So guys, if it says find inflection points, I know I got to find the second derivative, but your first step is always to take the first derivative, because you have to get that to get the second. So the first derivative here would be negative 3x squared plus 6x plus 9. Now my question doesn't ask for critical points, so I don't need to spend any more time on this first derivative. I don't have to set it equal to 0 or anything like that. I'm just using it to get to my next derivative. So I've got the first derivative there. Let's find the second by taking the derivative of the first. So I'm going to have negative 6x plus 6. So now that I've found the second derivative, I'm going to do this first part where I find the inflection points. So I'm going to set it equal to 0. And I'm going to solve for x. So this is an easy one, guys. This isn't x squared or anything. It's just an x in there. It's just linear. So I can just get x by itself. So let's subtract 6 on both sides. And I get negative 6 equals negative 6x. Divide both sides by negative 6. And I get positive 1 equals x. So positive 1 is where your inflection point occurs. So this is the x coordinate of inflection point. If I want to know the y coordinate of the inflection point, what would I do? Well, you guys, anytime you have an x and you want to find the y value, you take that x value and you put it into your original function. So what this is saying is on this graph, on the graph of the actual function, which is this, you guys, we're never graphing these. There's a point at x equals 1 where, remember, an inflection point is where it's going to change concavity. So it's changing concavity here at x equals 1. If I want to know what the y value is where it changes, I put it into the original function. So to get the y coordinate, I'm going to do f of 1. So negative 1 cubed plus 3 times negative 1 squared plus 9 times negative 1 plus 2. So 1 cubed is just 1, and there's a negative here, so it's going to be negative 1. 3 times negative 1 squared is positive 3. So plus 3 minus 9 plus 2. So let's see here. Negative 1 plus 3 is 2. Minus 9 is negative 7. Plus 2 is negative 5.
Mrs. Schatz.
Yes.
For for f of 1, like at the top of the when we started doing it, should like the 3 like negative 1? Should it be positive 1 instead of negative 1?
Oh yeah, I don't know why I made it negative 1. I'm glad you
I think
said
because of
that.
the first one.
Yeah, okay. So the first one I did right, and then I started putting negatives on my ones for no apparent reason. Yeah, I don't know why I did that, guys. Thanks for noticing. Yeah, just ones. You guys, our x is just 1. I'm not really sure why I started putting negatives in there. So let's see, what's that going to change? It's not going to change this 3, but it will change the 9 because it'll be a plus 9. Okay, so let's try that again. Negative 1 plus 3 is 2. Plus 9 is 11. Plus 2 is 13. How about that? All right, so our inflection point occurs at x equals 1, and the y value at that inflection point is 13. Okay, so I did that part. Check that off the list. Find all inflection points. And you guys, there's only one in this because our second derivative was just linear, so we just had an x to the first there. So we only got one solution. If you took the second derivative and it had a squared, for example, you'd probably end up getting 2 solutions and 2 inflection points. But this one, we just had the one. Okay, so let's look at what the next part is asking us to do. Find intervals of concavity. So remember when I made a number line on the 12.1, you guys, I'm going to do the same thing, except for this time, instead of putting the critical point here, I put the inflection point here. Remember, it's just the x value. I say, okay, the graph changes shape when x equals 1. I just need to know what's the shape on this side and what's the shape on this side. So you guys, concavity, remember, if you put a value in to the second derivative and it comes out positive, it's concave up, and then if it's negative, it's down. So this is exactly like what we did in 12.1, just we're using the second derivative now. I'm going to pick a point over here, and I'm going to pick a point over here, and I'm going to put them into the second derivative. So over here, something less than 1, let's use 0. So you guys, the second derivative evaluated at 0. So remember, your second derivative is this one, negative 6x plus 6. I'll get negative 6 times 0 plus 6, and that's just 6. So you guys, it's positive, which means the graph there is concave up. Let's test a value on the other side of 1. Let's try 2. So if I take the second derivative and evaluate it at 2, I get negative 6 times 2 plus 6. That's negative 12 plus 6, and I get negative 6. So it's negative on this side. So it's concave down. So what would my intervals of concavity look like? Well, I would say we have a concave up interval from negative infinity to 1. So you guys, this interval here, notice it goes from negative infinity all the way up to 1. And we have a concave down interval from 1 to positive infinity. So this side of the number line is concave down. So honestly, it looks a lot the same so far, right? We had to take the derivative again to get the second one, but once we had the second derivative, this was just like finding critical points, and this was just like finding increasing and decreasing intervals. We're finding different things, but we find them in the same way. So you're going to have some problems where this is exactly what you do. You take the first derivative so you can get to the second, and then you do all the stuff that you did in 12.1, but now you do it on the second derivative. So you're going to have some like that, you guys. But you guys, we can do even more with the second derivative. Let me get my list out. So this time we're going to work with this. And we're going to find even more things using the second derivative. So let's remember, I'm just going to make a new page, or I can scroll down. 2x cubed plus 9x squared plus 12x minus 5. So let's go down here. Let me get that written. Whoa, did my pen change color? I guess I did that with my finger on accident. Okay, 2x cubed plus 9x squared, I already forgot, plus 12x minus 5. All right, so here's what I want us to find on this one. I want to find critical points. I also want to find, I want to classify critical points. When I say classify, if you haven't seen it, ask for that yet. It means saying whether the critical point is a minimum or a maximum. So not only do I want to find them, I want to classify them. I also want to find the inflection points. And let's do the intervals of concavity again. I think that'll cover everything I want to find here. So notice these first two things I mentioned, we know how to do that with the, because that's first derivative stuff. But you guys, I'm going to show you a faster way to find, well, to find them is always the same. I'm going to show you a faster way to classify them using the second derivative. And then once we do that, we're actually going to be able to find this a lot easier too. So let's start the problem. You guys, it's chapter 12, which means the first step is take the first derivative. That's just kind of the theme of this chapter, is we take the derivative first. So let's do that, you guys. So the first derivative here is going to be 6x squared plus 18x plus 12. Now, I will need the second derivative at some point, but I can find that after I work with the first one. So, and you can find it right now if you want to and just save it for later. But like I said, I'm going to work with the first derivative first because it says I do need to find the critical points. So let's remember how to do that. That's where you take your first derivative, set it equal to 0, and solve for x. These are where we usually have to factor. So when I look at this problem, I think I could factor a 6 out of all of these just to make the factoring a little easier. If you don't, you can still factor it correctly. But I'm going to make it easier on myself and factor a 6 out of all of these terms. And remember, because this 6 doesn't have an x in it, it doesn't ever affect your x solutions. It's just on the outside now. So you guys, this should be a pretty easy factor, just plus 2 plus 1. So we get x plus 2, x plus 1. And then I set both of those values equal to 0. So again, this is kind of, you should be like, oh yeah, I just did this in 12.1, which you totally did. You guys, so I get x equals -2 and x equals -1. So remember what you just found are the critical points. So find critical points, done. If I need the y values for those, well, let's go ahead and find them. If I need y values at these critical points, remember you just take each one and put it in the original function. So let's find f of -2. So that'll be 2 times -2 cubed plus 9 times -2 squared plus 12 times -2 minus 5. Okay, so guys, when you cube something, the negative does not go away. So it's going to be 2 times -8 plus 9. This will be a positive 4. We'll have -24 minus 5. So -16 plus 36 minus 24 minus 5. Let's see, 20 minus 24 is -4 minus 5. I think it's -9. So you guys, your first critical point occurs at -2. And if you need to know the y value there, if it asks for it, it's -9. Your second critical point happens at -1. Let's find the y value. Plus 9 times -1 squared plus 12 times -1 minus 5. All right, so -1 cubed is -1. So this is going to be -2. This is going to be plus 9. This is going to be minus 12 minus 5. -2 plus 9 is 7. Minus 12 is -5. Minus 5 is -10. Does that seem right? I guess so. Yeah, plus 9. All right, looks right. So your critical point at -1, -10. All right, so we found critical points. Now we have to classify them. And you guys, if we were in 12.1, from this point, I would start making a number line, right? And I would put my 2 critical points on it, and I would test these intervals. That would get me the answer. It definitely would, you guys, but that is not the way we're going this time. From here, after I find the critical points, I'm going to go ahead and take that second derivative. So let's do that. So the first derivative is here. If you take the derivative again, you'll get the second. So what would we get there? 12x plus 18. So what am I going to do with the second derivative? Well, let me show you. After I get the second derivative, I am going to test my critical points this, and this, I'm going to put them in the second derivative, and the second derivative is going to tell me if they are a min or a max. Remember before I had to look at that number line and I had to test all these values to see what was happening around the critical points, and that's how I could tell if things were a min or a max. But you guys, if I have a way that takes less time, I'm going to do it. So let me show you what I'm going to do instead. This is called the second derivative test, and it is a way to classify critical points. I don't know why I said it like that. That was weird. Okay, so put your first critical point into the second derivative. Here's what I get. 12 times -2 plus 18. And I get -24 plus 18. And my answer here is -6. Remember what the second derivative tells you. If the second derivative is negative, it means your graph at that point is concave down. So here's the point. Here's the graph around it. Is this a min or a max? Well, you guys, it would have to be a max.
Can you scroll down?
Is that better?
Yes, thank you.
Okay. So the thing about the second derivative, when it tests concavity and testing the shape of the graph, if you test the shape of the graph at your critical points, you will know if they're a min or a max. So what I found here was that my second derivative at -2 was negative. It has to look like concave down there. Let me make that a little better. It has to be concave down there because that's what the second derivative being negative means. So if this is your critical point and your graph is concave down around it, that has to be a max value. So without even looking at a number line, I can say that there is a max at the critical point -2, or if it asks for both coordinates, it happens here at -2, -9. Let's see what the other critical point is. You guys, the -1. Put that into your second derivative. You'll get 12 times -1 plus 18. That's -12 plus 18, and we get +6. So at this critical point, where x equals -1, the graph is concave up because my second derivative was positive, which means that this critical point has to be a min. So we have a minimum at the point where x is -1 and y is -10. So it's just a faster way because we know about concavity and we know how to read the second derivative. We don't have to do that first derivative test with the number line anymore. We can just find your critical points and put them into the second derivative. And as long as we remember how to interpret, you know, which one's up, which one's down, you can classify a lot faster. So let's go back up and see what we've done so far. We found critical points and we've classified them. I have not found inflection points or intervals of concavity on this one though. So let's go back down. Remember that inflection points come from the second derivative set equal to 0. So that's not going to be too hard. Let's do that part. So remember the second derivative was 12x plus 18. Set it equal to 0. So 0 equals 12x plus 18. Solve for x by subtracting 18 on both sides. So -18 equals 12x. Divide by 12. So we get x equals -18 over 12, or let's reduce that to -3/2. So this is your inflection point. Being -3/2, usually yours don't come out to be fractions. If you did need to find the y value, just remember, even though you're all the way down at the second derivative, If you want to know the y value of this inflection point, you would still put it in the original function to find the y. But on this one, I'm not going to have you do that, but you could. Yours that you do that on are a little bit easier because they don't turn out to be fractions. But you guys, now that I have my inflection point, I need to find the intervals of concavity. So remember, like I did on that last problem, I do need to put the inflection point on a number line because I don't have another way to do that. So we just learned the second derivative eliminates the need for our number line on the critical points test, but I don't have a better way here. So you guys take your inflection point, put it on, and here's the beauty of this part, guys. I need to test a value here and here in the second derivative. I think I've already done that. You guys, would you agree that the critical point that we already found and tested at -2 is on this side of -3/2? And the critical point that we already found and tested, the one at -1, would be on this side of 3/2? So you guys, once you get down to this point, if you've already classified your critical points, you can use those values when you look for the intervals of concavity. So what did we find about concavity at -2? So remember, we put that into the second derivative. We found that it was concave down at -2. So make that note on your number line. What did we find when we put we put -1 into the second derivative? We already found that it was concave up. So you guys, if you have to go through and find all of these things, you know, once you get to this point, you really do have all the info you need already. So yeah, just use the values at your critical points to classify the intervals of concavity. So what does this mean for our intervals? Well, it means that we're concave down from, let's see, -infinity all the way up to your inflection point of 3/2, or sorry, -3/2. And you're concave up from -3/2 to +infinity. So we found a lot of things on this problem. Let's summarize what we found. We found crit points. We found them at -2, -9, and at -1, -10. We classified those points using the second derivative. We found that this one is a minimum and that this one is, sorry, backwards. We found that this one is a maximum and this one was a min. And remember, we put them into the second derivative to find that. We looked at the shape. We found inflection point. There was only one. You guys, usually there's one on your examples just because of the functions we start with. So the inflection point for this one was at x equals -3/2. I did not find the y value there, but you know how if you would happen to need to, you just put it into the original function. And then I found concavity intervals. So I found these. I just wrote them, so I'm probably not going to write them again. But I'll put that on the list, and that's what they are. So you guys, we could basically graph this, you know, just by knowing what we know at this point. You don't have to, but we know a lot of information about this function. On your homework problems, there's not a problem that asks for all of these things at the same time, but it's going to ask for one thing or another, or a couple of things. So you do need to know how to find it all. And I like to find it all on at least one problem because you really get to see how it's all connected, you know, how you use one thing to help you find another thing. So let's do one of those other examples that I have written, and ready. It was on this page. Ooh, this one. Let's do this one. We got some chain rule in there. All right. We're going to find everything on this one. You guys, this one's different the way that it's written, right? It's not just going to be power rule finding the derivative. We're going to have chain rule, but it's going to be fine. It's not going to be as bad as you think. So 3 times x minus 2 to the 5th. Oh, I made a new page. That's fine. Ooh, I made lines big. That's too big. Okay. All right, so f of x equals 3 times x minus 2 to the 5th. And I want to find all the things, you guys, critical points, inflection points, you know, the whole 9 yards, which means I got to take the first derivative. So you guys remember the chain rule. It might have been a while since you used it on one just like this, but you bring the 5 down in front with the 3, and that's going to make a 15. You leave this the same and you take a power off. And then now the chain rule part, remember it says that you have to take the derivative of what's in here and tack it on. Luckily for us, that's just 1. So the first derivative is just 15 times x minus 2 to the 4th. So we got the first derivative pretty easily. And you guys, even though it doesn't look like it, because it looks like we've got a term to the 4th in there, which we absolutely do, finding the critical points on this one is actually super easy. What happens when I set this equal to 0? Well, you guys, x minus 2 to the 4th, you could think about that as 4 separate factors of x minus 2. You really don't need to. You guys, the reason I want to show it like this is that how do I solve an equation that equals 0? I set all the factors equal to 0. So now the 15, it's just like that 3 or the 6 we had in the other problem. It's not affecting your solutions for x because it doesn't have an x in it. But you guys, I just need to set all the factors equal to 0. They're all the same factor. So you guys, all you have to do is set this x minus 2 equal to 0 one time. It would be overkill to do it 4 times and get the same solution 4 times, right? So you guys just take this. This is the only factor we have, set it equal to 0, and we have 1 critical point. Okay, so here is our critical point. I would like to classify it, but I need the second derivative for that because I really don't want to have to use the first derivative test. So let's find the second derivative. Okay, second derivative. So from the first derivative here, using the chain rule again, we have, this will be the 4 coming down with the 15. This will be 60 times x minus 2 cubed. And again, the chain rule part, because the derivative of this is just 1, it's really not there. It is there, but you don't have to write it. So second derivative, that was pretty easy to find. And I want to use it to classify my critical point. So let's see what happens. Oh, that's where I put the 2. So you guys, you're putting your critical point that you found into the second derivative. What happens here? You guys, this becomes 0, which makes the whole thing 0. So guys, if the second derivative is positive, we're concave up. If it's negative, we're concave down. If the second derivative is 0, you guys, this is indeterminate. You guys, I can't say, oh, it's up or oh, it's down. Let's talk about why it's indeterminate. Interminate, guys. How old am I? What grade am I in? You guys, if you get a 0 here, it's indeterminate. Reason being, first of all, what?
I'm so sorry. I apologize if I missed it. Why is it 0? 6 when,
So it would be 60.
oh,
And then
times 0. Okay.
Yeah,
To 2 minus 2. I'm sorry. Thank you.
that's okay. Thanks. Okay. So here's the problem. It's not concave up or down there because 0 is not positive or negative. When the second derivative equals 0, don't I have another word for that point? Doesn't this mean that 2 is an inflection point for the second derivative? I didn't even have to solve for it. It just fell in my lap. What does an inflection point mean? It means it's a place where it changes from concave down to up or vice versa, which means it's neither at that point. So let me show you an example of what's happening here. It's kind of hard to draw. Okay. This would be like the point at x equals 2. It's a critical point, but it's also an inflection point. Can you see the change here? And you guys, the critical point part of it is so subtle because it doesn't look like it's changing from increasing to decreasing. It looks like it is increasing, goes through a critical point, and then keeps increasing, which is exactly what happens, guys. This critical point / inflection point is one of those rare cases, guys, that remember when we were doing our number lines and I said, just because you get a negative over here doesn't mean this will be positive because things happen. You guys, this is the thing that's happening. You guys, on both sides, it's increasing. So you guys, I saw a problem like this in your homework and it freaked me out a little bit. Let me see. A critical point comes from setting the first derivative equal to 0, and an inflection point comes from setting the second derivative equal to 0. So anytime you need critical points, you're thinking first derivative. Anytime you're needing inflection, that's second derivative. So you guys, our second derivative test doesn't help us here because it's indeterminate. Like I said, if you get a 0 and you can't say if this is a max or a min still. And you guys, it's really not either, right? You guys, this is not a max point because it's not going from up to down, but it's not a minimum either because it's not going from down to up. So you guys, if you happen to get something like this, I hope you don't. I tried to keep this type of question out, but MATLAB randomizes numbers and stuff, you know, when you have your homework. So if you get something like this, there should be like where you can click that it's indeterminate or something like that. It still has a critical point that you can put in. It still has an inflection point. They're just the same. They're the same point. So hopefully you don't come up with it. And if you do and have trouble with how to answer that, let me know. Let's see. So yeah, that one is short because we can't really go anywhere. Now you could talk intervals of concavity on this one. You guys, you'd have concave down on this side of 2 and concave up on that side of 2. But other than that, there's not really much else you can say about this graph. It's just one of those rare cases where critical point and inflection point are the same. And there's, like I said, you can't really say this is a min or a max. And that's okay because your question should allow for that. And if it doesn't, and you come up with one like that, then I can help you. Let's look at this one. This will be the last thing. It should be pretty quick. You guys, I have f of x equals 4x squared plus 16x. Okay, so this is my original function. I want to find as much as I can about it. So critical, inflection, all the good stuff, you guys. Let's take the first derivative. So I get f prime of x would be 8x plus 16. While we're here, let's go ahead and set that equal to 0 to find the critical point. So 0 equals 8x plus 16. You guys, we don't have to factor anything on this one, right? Because this is just x to the first. Let's just subtract. So I get negative 16 equals 8x. Divide by 8. And I get x equals negative 2. You guys, this is our critical point. Now that I have it, I want to test it, but I want to use the second derivative to test it. So I'm going to go here and find the second derivative so I can use it. You guys, so from the first derivative, take the derivative again, and you'll get the second derivative is just 8. So you guys, look, our second derivative doesn't even have an x in it. Don't let that scare you. This is just another more odd type of question I want to make sure you're prepared for. So remember how to classify a critical point is I take the critical point x value and I put it into the second derivative. But you guys, how do I put negative 2 into a constant function 8? Well, remember, you can't, there's nowhere to put the negative 2 here because there's not an x in the problem. All this is saying is that the function at negative 2 is positive 8. You could put any number you want in there, and it just means that the function is, the second derivative here is always 8, which means it's always positive, which tells me that this, both at negative 2 and throughout the entire function, is concave up because the second derivative is positive. So I can still classify my critical point, even though there was nowhere to put this negative 2 into the function. A constant 8 just means the second derivative is always positive 8, which means this function is always concave up. So your critical point would be a minimum. Now, as far as what about an interval of concavity? I already found out that my function is always concave up. So you guys, we would only have one interval, and it would be that it was concave up for the whole thing, from negative infinity to positive infinity. It also means that there's no inflection points, obviously, because inflection points are where it changes. Concavity, we don't have a change. But you guys, if you tried to set this second derivative, which is just 8, equal to 0, you could see there's no inflection points here. That doesn't make sense. So on this one, really, once you find and classify the critical point, you could have an interval of concavity too, but that's all you can do on this function. And you guys, you do have some that might end up kind of weird like this, and I don't want it to throw you. It should be a little bit more simple, honestly, because it's less work on the problem. But you guys, that's the kind of things you're going to see. You guys, the examples that I did with you are hopefully going to prepare you for that next homework. And remember, that's not due on Sunday. But the ones that are due on Sunday are just finding second derivatives. So we got a little bit more practice with that today too. I will say, I want to say probably the hardest thing that I put on the homework you have for Sunday was probably a product rule or two. So you guys, you're just going to have to be careful. Sometimes when you use the product rule to get the first derivative, you might have to use it again to get the second. You might have to use it multiple times to get the second because you might have two different products then. Just keep in mind that if you have the product of two things and you can't actually multiply them together, that's when you want to use the product rule. I don't think I gave you any quotient rules. I gave you a natural log, which, like we saw in class Wednesday, once you take the first derivative, then you will have a quotient, and you might have to use the quotient rule after that, but I didn't give you one that starts with the quotient rule. Other than that, they should be pretty mild. just make sure you understand the concept of the second derivative. It's just taking the derivative of the first. And then I can always answer more questions if you come up with them in this next homework. I could do that even on Monday since that's not due till next week. Okay, so I think that's it. So guys, I will see you Monday then. Same time, same place.